Welcome to the TOEFL listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Patel. Thanks for meeting with me during office hours to talk about my project on offshore wind farm optimization.
Good afternoon, Maya. Tell me about your focus. Are you concentrating on turbine placement to maximize energy yield?
Yes. My advisor suggested I look at layout optimization and wake mitigation strategies together. I am trying to balance array spacing, wake steering, and electrical cost to maximize AEP per dollar.
That is a good scope. Start by clarifying your objective. Is the primary goal maximizing annual energy production or minimizing levelized cost of energy while keeping production high?
I want a multi-objective approach. The main performance metric will be AEP, but I will include LCOE as a constraint or secondary objective so that spacing or cable length does not make the design uneconomical.
Excellent. For turbine placement, the key technical issues are wake effects, wind resource variability, and seabed constraints. Which wake models are you planning to use for optimization?
I planned a hierarchical strategy. First, use a fast engineering wake model like Jensen or the expanded Park model to screen many layouts. Then use a surrogate model, such as a Gaussian process, trained on a set of high-fidelity simulations. For final validation, I will run LES or RAN-SCFD on a few candidate layouts.
That approach balances computational cost and fidelity. Remember, the engineering models can misestimate complex wake interactions, especially in large farms. A surrogate that captures nonlinearities will help the optimizer avoid local minima.
I was thinking of using a genetic algorithm for the global search because layout space is non-convex. But I worry about runtime. Do you think combining GA with the surrogate is sufficient?
Yes. A common practical pipeline is to run GA with the fast wake model to explore broadly, then refine the best candidates with the surrogate informed by high-fidelity runs. That reduces evaluations of LES to a handful.
When we talk about spacing, what guidelines should I use as starting points? I have seen 7 rotor diameters downstream, and about 3 to 4 diameters crosswind mentioned in literature.
Those are reasonable initial values. In offshore farms with very large rotors like 190 meters, designers often use 6 to 8D downstream and 3 to 5D laterally. But optimal spacing depends on the wind rows and economic trade-offs.
Right. In my case study, I am using 10 megawatt machines with 190 meter rotors in a North Sea area. The prevailing wind is from the southwest and there are seasonal shifts. How should I account for wind directionality?
Incorporate a directional wind rose into the AEP calculation. The optimization should weight layout performance by the frequency and speed distribution for each direction. Also consider extreme directional shears since it can change wake deflection.
About wake control strategies like wake steering and induction control. Is it better to optimize placement first and then design control, or co-optimize both?
Co-optimization is ideal because wake steering changes downstream flow, so the best fixed layout might not be optimal under active control. However, co-optimizing increases complexity. A practical compromise is to optimize layout assuming baseline controls, and then optimize controls for the final layout.
I see. I read a case where combining layout optimization and wake steering reduced wake losses significantly. Do you have a sense of how large those savings can be?
It varies. In medium-sized farms, wake losses can be 15 to 30%. With coordinated layout changes and wake steering, you might reduce total wake losses by several percentage points. In one North Sea case study, we reduced wake losses from about 25% to 16% by using layout changes and wake steering together.
Reducing losses by 9 percentage points would have a big impact on AEP and revenue. But that probably increases electrical or installation costs.
Exactly. Wider spacing reduces interference but increases cable length and may force turbines into deeper water with higher foundation cost. That is why you must include cost models. Cable routing and substation placement can be optimized simultaneously to contain costs.
For cost modeling, should I use simple per kilometer cable cost and fixed substation cost estimates, or seek more detailed electrical loss modeling?
Start with per kilometer costs and transformer costs to keep the optimization tractable. Then add electrical loss modeling so you can estimate power losses in cables. Losses affect AEP slightly, but matter for very large arrays.
I am also concerned about environmental and navigational constraints. How are these treated in layout optimization?
Treat them as hard constraints. Exclude turbine placement in shipping lanes, protected habitats, and buffer zones. The optimizer should only consider feasible locations. You can encode forbidden polygons in the layout representation.
One more question about wake modeling. When I calibrate the surrogate with LES samples, should I sample more densely in the wind directions that dominate the windrows?
Yes, adaptive sampling that focuses on high probability directions and on regions of design space near promising layouts improves surrogate accuracy where it matters for AEP.
Thank you. This helps a lot. For my project plan, I will implement a GA with an engineering wake model, train a Gaussian process surrogate with LES runs selected adaptively, include simple cable cost and exclusion zones, and then evaluate the best designs with high-fidelity CFD and full cost accounting.
That sounds robust. Also document assumptions like turbine power curve, wake model coefficients, and maintenance considerations. Those details affect the final AEP and economic conclusions.
I will. Do you think I should include a sensitivity analysis on rotor diameter and rated power?
Yes. Sensitivity to turbine size, spacing, and control strategies will strengthen your conclusions and show when layout choices are equipment dependent.
Great. I will prepare an initial results set and come back in 2 weeks. Thanks for the guidance.
You are welcome, Maya. I look forward to seeing your results.
Listen again to part of the conversation, then answer the question.
In one North Sea case study, we reduced wake losses from about 25% to 16% by using layout changes and wake steering together.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit spinta.org.